Welcome to Yen-Chen's defense. Yen-Chen has done a really cool PhD on neural fields for robotics and robotic manipulation. And Yen-Chen's actually been one of the pioneers in this area. So NeRFs came out right about the start of his PhD, and he was one of the early adopters. But back then, these models, these neural fields, these neural radiance fields, were mostly just for graphics. And Yen-Chen was one of the first people to realize that they could be used more generally as a scene representation and have applications to perception and robotics. And he really focused on that for his PhD. So we'll get to hear about how that all works in a minute. Yen-Chen's also, I just want to reflect on his time briefly. He's been an amazing presence in the group, in both my group and Alberto's group. So I'm co-advised with Alberto Rodriguez. Vincent Sitzman is on the committee. He's on Zoom. And Yen-Chen was technically my first student when I arrived. So he was the first one to start. And because of that, and because I didn't really have a background in robotics, he had to figure a lot more on his own than I think a normal PhD student. So he was the one that set up our robotics hardware. He was the one who found out, what even the robotics conferences are. That was all new to me. And it wasn't always easy early on. He had to do it himself. But then Alberto joined, and things have been pretty smooth since then. We had an actual expert with us. So it's been great to all work together. And the other thing that I really have enjoyed with Yen-Chen is that he's just always full of new ideas and excitement to try the new thing. And at every meeting, he teaches us something new. I've learned about hardware optimization and language models. And there's, aside from his main projects, there's so many little side projects. One of my favorites was we went on a lab ski trip, and Yen-Chen had his GoPro on the slopes, and I wasn't sure what he was doing, but it turns out he was scanning the ski slopes and intending to make a NeRF of the entire mountain. It didn't quite work out, but he got some pretty cool panoramic videos from that. Okay, so it's just been a pleasure to have you in the group, and I think that without further ado, we can get started. So Yen-Chen.
Okay. Thank you, Phil. Okay, hello everyone. I'm Yen-Chen Lin, and today I'm going to present my thesis on neural fields for robotic manipulation. So now we're living in an exciting time for robotics. In safety critical domains, such as self-driving cars, photorealistic simulators can generate new paths of dangerous scenarios that are not safe to collect in the real world. For perception, we have machine learning methods that, given an object's 3D model, can accurately estimate its pose even under occlusion. For verifying ideas or sim to real, we have various scalable simulation tools to prototype or build our robotic systems. These are all amazing technologies that have advanced the field of robotics in the past few years. However, despite the amazing capabilities of these tools, they all have one common requirement: 3D contents. And the issue is 3D contents are hard to acquire. In many cases, 3D contents that are functional for robotics data generation or simulation are not accessible. For example, one way of creating high-quality 3D content is to ask artists to generate them. However, for professional artists, it takes around 70 hours to create this pair of shoes on the left. Another solution is to use high-end scanners, but the devices are expensive and hard to maintain. So given how hard it is to create 3D contents, if we look at this screenshot of a video game and try to put price tags and all this stuff, this is what we're going to see. So you can see that everything that's digital 3D is pretty expensive. This character is more expensive than a few GPUs, which is pretty crazy. On the other hand, accessible 3D contents may not be functional. For example, one can use an RGBD camera to scan the environment or objects of interest. However, the depth sensors have limited resolution and struggle to capture reflective or thin objects, as you can see on the right. So to address these problems, my research goal is to create functional 3D content with accessible cost. And of course, what I mean by functional here is application dependent. And in this talk, functional means it is useful for certain robotics applications. So if we create a plot where functional is the x-axis and accessible is the y-axis, human artist and 3D scanner can be placed at the bottom right, because the created content is functional, but the cost is inaccessible. RGBD camera can be placed at the top left, because the created contents are accessible, but not always functional. And my goal is to reach the top right, where we can create functional 3D contents for robotics easily. And as a researcher, I wish my progress looks like this, which is linear and stable, stress-free, work-life balance, everything. However, we all know that in reality, research progress looks more like this. But luckily, thanks to my advisors and collaborators who stopped me from falling down many rabbit holes, I was able to actually go through this rather smooth route during my PhD. So my research on neural fields for robotics actually started from my open source PyTorch implementation of NERV on GitHub. Now you may be curious, what is NERV? Well, NERV stands for neural radiance fields. So it takes in a set of input images to create a 3D representation that can synthesize novel views of the scene. NERV represents the scene as a neural network that maps 3D location, XYZ, and view direction, theta phi, to RGB colors and density sigma. It then uses volume rendering to render a pixel. This rendering process is fully differentiable, allowing us to optimize the neural network by minimizing the reconstruction error from rendering arrays. So how can a 3D representation that renders photorealistic images help robotics? Our initial exploration leads us to explore iNerv, inverting neural radiance fields for post-estimation. To understand how iNerv works, let's take a closer look at NERV's optimization procedure. During training, NERV would use training images camera pose T to generate rays R as inputs to the neural network F theta. And the neural network will then output color and density for volume rendering. The results will then be used to compute the loss for each pixel and backpropagate the gradient to the neural network parameters data. One thing to note here is that since camera poses affect how the rays are formed, NERV is very sensitive to any error in the camera poses. However, camera pose errors are almost inevitable because it is impractical to expect the structure from motion or SLAM system to output perfect localization results. So to let NERV also work well with imperfect camera poses, one interesting observation we can make here is that the step that converts camera poses to ray is also differentiable. Therefore, one can actually backpropagate the gradient all the way back from the render pixel and the ground truth pixels to the camera poses for post-estimation. To test this idea, I'm going to show you how this looks like when a NERV is already trained, and the goal is simply to figure out an input images camera pose T. So here on the left, we show how estimated camera pose that is colored in gray gradually converge to the ground truth camera pose that is colored in green. And on the right, we show the overlap of the image whose pose is unknown and another image rendered by NERV using the current estimated pose. When the optimization procedure is done, these two images will overlap perfectly. And here's the diagram to show that when the two images overlap perfectly, the rotation error indeed reduced to 0. And here are more qualitative examples of the same procedures. You can see that this procedure is actually pretty robust. It works even when the initialized rotation of the estimated camera pose is off by 45 degrees. So to further test its limit, we decided to try it on a popular post-estimation dataset called LIMOT, and here are the quantitative results. Although iNerv did not outperform state-of-the-art, and that leads to my CVPR rejection, it achieves competitive performance without accessing to any 3D mesh models of objects. So I still think it's pretty cool. So the above results are obtained when a NERV is already trained. A natural follow-up question is, can we jointly optimize the input camera poses T and the neural network parameters data? This optimization procedure can potentially correct the input camera poses when they have errors. So in this figure, this is another experiment in our iNerv paper. X% represent the portion of ground truth camera poses that are used to train NERV. So our results highlighted in the red box show that with the iterative post-estimation and NERV optimization, training a NERV with only 25% of the ground truth camera poses can get results that still look photorealistic and is comparable to a NERV trained with 100% of the ground truth camera poses. In comparison, A nerve trained with only 25% of the ground truth camera poses without the iNerv optimization procedure show obvious artifacts in the render image. Since the publication of iNerv, the idea of backpropagating the gradient to the camera poses have now become a common trick. It has been used or extended by multiple other works for SLAM, navigation, or city scale reconstruction. Notably, other works in the community like BARF or nerf minus have further shown that it's possible to optimize the radiance field even with 0% of the ground truth camera poses. This line of research presents an exciting opportunity to remove the structure from motion preprocessing. Okay, so that's iNerv. It's pretty simple, and it's our first exploration on using neural fields to help robotics. It makes creating nerves more accessible by making it less susceptible to camera pose errors. It also makes neural fields more functional by showing that we can use it to perform object pose estimation, although not state of the art. However, using iNerv is slow, and it does not generalize to object instances that are different from our nerves. So this leads us to enter a phase where our main goal is to make nerve even more functional for robotics. And the project that came out is nerve supervision, where we use nerve to generate synthetic data for dense correspondences. So in this project, we show that by using nerve as the supervision signal to train a dense correspondence model, the robot can accurately localize the same part of the fork at different poses to perform accurate 6-degree freedom picking. This task is hard for previous methods like dense object nets because they mostly rely on RGBD sensors to automatically annotate correspondence, as correspondence is very hard for a human to annotate as go. However, many objects like common kitchen items are reflective and don't work well with RGBD cameras. As an example, here you can see that the RGBD camera perceives the incorrect geometry of forks as highlighted in the red box. So the advantage of our proposed method, nerve supervision, is that it's a pipeline for generating correspondence data with RGB-only sensors. And it works better than classic techniques like multi-view stereo, as we'll show later. So nerve supervision consists of 3 steps. First, we need to create a nerve of the object that we're interested in. So we start by collecting multi-view RGB images of the object. And here you can see me rolling on the floor. You don't need to do that. It's just that I couldn't find a table at the time. So this step can be completed with the cell phone. So the cost of achieving this step is very low. Then we apply structure from motion to recover the camera poses and the sparse point cloud of the scene. Here, you can see that points are mostly on the floor. And that's because this object is very challenging for structure from motion or multi-view stereo to really reconstruct. But even with the sparse point clouds on the floor, it actually can help nerves optimization. So although the original nerve formulation only requires post-RGB image as supervision, we found that incorporating supervision from the sparse point cloud mitigates the noise caused by the moving shadows during the image capturing process. And on the right-hand side, here we visualize the RGB and depth images rendered by the nerve model. For comparison, here we visualize the depth map predicted by CoMap, a widely used multi-view stereo library. The estimated depth map is low quality because the thin and reflective nature of common kitchen items, again, makes it challenging for multi-view stereo to match pixels based on patch similarities. Now, the second step of our pipeline is to generate a dense correspondence dataset from nerve. We'll use 2 views to explain the idea, but it can be easily generalized to multiple views. First, we use nerve to synthesize 2 RGB images of the scene. For clarity, let's zoom in on the left image. If we shoot a 3D ray into this magenta pixel, it can be visualized as the 2D epipolar line on the other image. And now we're also zooming on the right image as well to explain the following steps. Along the 3D ray, we can sample points and use nerve to predict their corresponding densities. So sample points here are shown in green circles. The larger the circle, the higher the predicted density. In this case, of course, we don't just sample 2 points. We actually sample a lot of points along the ray. But by just performing some very simple thresholding, there are only 2 points that remains. The original NERF strategy is to use the weighted average of these 3D points based on their densities to derive the depth and the correspondence. However, we show that this strategy leads to the wrong depth, visualized as the red cross. So this result shows that the original NERF's formulation of getting depth is not functional for the task of correspondence generation. To avoid this issue, we propose to keep all the sample points and sample them as correspondence probabilistically based on their densities. For example, here, if the green circles, the larger one have density 0.8 and the smaller one have density 0.2, then 80% of the time we'll sample the larger green circle pixel as the ground truth correspondence, and only 20% of the time we'll sample the smaller green circle as a ground truth correspondence. And after further experiments, there are actually other heuristics that can make it work. For example, you can select the first points whose density exceeds the certain threshold from your camera array. That will also work, but then will result in slightly worse performance. Okay, then the final step of our pipeline is to train a dense correspondence model. We use a fully convolutional networks trained with contrastive laws to predict dense features for correspondence matching. Specifically, we use NERF to synthesize multi-view images and use step 2 to derive the sample pixels correspondence in the other image. Then we crop the patch around the pixel and use the contrastive loss to encourage the corresponding pixels features to be close. This process is visualized as the green dot on the right. To complete the contrastive loss, we also sample the negative pixel randomly and encourage its feature to be different. So this step is visualized as the red dot on the right. The overall loss function is shown in the bottom left, where the L match basically means we want to get the features of the 2 green pixels and make them as close as possible, while the L unmatch basically means we want to get the feature of the green pixel and the red pixel and make them as far as possible. So after the correspondence model F is trained, we can use it to predict dense descriptors given an input RGB image. And at this stage, we do not need the NERFs anymore. So here on the left, we show the input RGB image, and on the right, we show the segmented RGB image and the dense descriptors predicted by our correspondence model F. You can see that similar parts of different objects have similar features. So that means our correspondence model can now predict the same feature, let's say for the fork's tip, even for different forks. Since the descriptors are dense, we can arbitrarily select key points and track them. In these examples, we show 3 key points that are colored in red, green, and blue. We know that this is more flexible than most key point detection methods because we can select which key points to track during the test time. To demonstrate that the pipeline can accurately predict dense correspondences, here we show that the tracked 2D key points with stereo image pairs help us derive the 3D locations and 6-degree freedom grass poses for accurate picking. And notably, in this example, we do not have NERF models for any of this fork, but the learned correspondence model can generalize at test time. So this enables our robot to manipulate forks that are not seen in the training data. Okay, of course, this pipeline doesn't just work on forks. One can also reuse the same pipeline for other challenging objects like strainers. And here we show that the robot can collect strainers from the dish rack with, again, 6-degree of freedom picking. And I know you probably think the strainers looks pretty weird in this context, but this is actually my true motivation of doing this project. Because at that point in time, I was doing a lot of hot pot with my partner. And we always use strainers to grab the fish or the shrimp. So I was thinking, maybe I can make a robot to use the strainers. And until I tried it in the lab, then I realized, oh, RGB camera cannot see this. And this actually motivates this whole line of research. So that's why strainer is actually not weird. It's very practical. So that's NERF supervision, a pipeline that uses NERF to generate synthetic data for object-centric robotic manipulation system. Well, another interesting way to expand neural fields functionality for robotics is to think of them as virtual cameras that can generate images not just at novel views, but also with novel camera models. And that leads to MIRA, mental imagery for robotic affordances. So the key insight here is that we can train nerves using perspective camera model, as you can see here on the top, as most of the training images are perspective images. But after training, we can freeze the nerve weights and simply just replace the perspective camera model with an orthographic camera model to render orthographic images. So you may be confused. Why do we want to do that? Well, it's because orthographic images is a visual representation that works very well with affordance model, which is a type of robotic system that takes images as input and predict pixel-wise action value that represents how good it is to perform a motion primitive at that specific pixel. The final action is then decided by a spatial argmax operation. So here's the comparison. If our affordance model takes the perspective images on the left as input, it would need a large-scale data set to actually understand object distortions caused by the perspective camera. On the other hand, if our model takes orthographic images on the right as input, where each pixel represents a fixed unit of 3D space, it means that the model doesn't have to waste parameters to build invariances to object distortions. So it can allocate the extra capacity to learn features that generalize better. Also, simple data augmentation strategies like applying rotations to the orthographic image will simulate physically reconfiguring the scene and increase the size of the data set. So this is actually a very crucial trick for a domain that usually does not have large-scale data sets like robotics. Okay, so with this insight, here's how our method MIRA works. MIRA represents the scene with a neural radiance field. Before each action, it takes in multi-view RGB images as inputs to optimize a nerve of the scene. And by using instant NGP, the nerve optimization can be completed in around 10 seconds. Now, comparing to the existing affordance methods that predicts 3 degree of freedom actions from a top-down orthographic image computed using RGBD camera, MIRA actually doesn't rely on RGBD camera. We can predict 6 degree of freedom actions using novel orthographic images synthesized by nerve in tandem with the affordance model. It then compares each novel view's best action value to decide the best pixel and the best view. Now here we only show 2 views for the illustration purpose, but in our actual system, we actually render 100 views and send all the novel orthographic views to the affordance model, predict the action value, and then do the spatial argmax over all the views. Now, after we select the best pixel and the best view, we can use the best view's viewing angle to parameterize the 6 degree of freedom actions roll and pitch. Then we can use nerve to predict that specific pixel's depth to determine the action Z. And with that, we're able to synthesize 6 degree of freedom actions. And here is an illustration of our policy in simulation. So how does it work in the real world? Now, all the following clips that I'm going to show you are from a policy that's trained with 10 demos for the task. So the first task is to place the floss into the container. Again, you may think this is such a weird task, but actually I'm very happy with this result. It's because during my internship at Google, this is actually what they want to do a lot. But RGBD camera or a laser scanner couldn't really see the transparent objects. And so as you can see at the bottom right, they have to paint the transparent containers in order to do the demo. And so it is very satisfying to finally see that with neural scene representation or neural fields, we can perform this kind of robotic manipulation tasks. And here are just more footages of the same task at different configuration. And here I want to highlight that actually you can see that there are multiple slots for the robots to actually insert the floss. And that means the action space for this task is actually multimodal. And our formulations actually be able to handle that. Here, the second task is to place the metal ball into cups. And this task is challenging, again, because the object is reflective and the container is transparent. I want to shout out to Wei Chu for giving me an idea of this task, because before he told me, I don't really know anything about this steel metal bowl thing. And he told me that rich people all use this steel metal bowl to drink whiskey. And this morning, out of curiosity, I read it, and it turns out everybody hates it. So maybe don't buy it as a gift, or just don't buy it if not for research. And here are just more footage of the same task. And here, what's different is that we show that our method can actually generalize to some cups that are not seen during training. So our method can actually generalize to different instances. Cool. So to put our work into context, compared to existing affordance methods, form to fit and transport networks, our methods only need RGB cameras, and it can handle reflective or thin structure objects, and it also supports 6-degree of freedom actions. So here is just some comparison against the baseline in the simulation. And you can see that our policy supports 6-degree of freedom actions, while transport network and form to fit struggles. And here, transport network SE3 is actually a variant of the original transport network paper, where they additionally train an NLP to predict the remaining 3-degree of freedom in order to achieve, in order to predict 6-degree of freedom actions. And you can see that by just training an NLP to perform this task, the success rate is still relatively low. And here is another task where we want to put the L-shaped cube into its slot. And again, our method is able to achieve competitive accuracy, while transport network SE3 and form to fit struggles. And here is another task where our goal is to place the red cube in the green bowl. And again, our method can work even when the environment is rather cluttered, while the baseline transport network SE3 and form to fit does not work well. Okay, so that's Mira, a method that uses neural fields to help robotic affordances through virtual camera. And so far in this talk, we have been mainly focusing on small-scale tabletop scenes. So to be more ambitious, let's see if we can use neural fields to build a 3D world model for embodied agents that can move around. So to achieve this goal, we extend instant NGP and propose modular NGPs. So instant NGP is an algorithm from NVIDIA that can be used to speed up NERF by 1,000 times. So artists around the world have been using instant NGP to capture these stunning scenes. However, most of these impressive results are in small-scale scenes, which focus on specific objects of interest. So what if we want to reconstruct an entire building or even an entire town with enough detail so that we can simulate any street corner and make our robots feel like they're actually physically there? Would instant NGP work? To test it out, let's try it on a cityscape dataset. Here's the results of instant NGP. And obviously, it doesn't look as good as the previous stunning NERF scenes. So what's going on? To understand the problem, let's use this 2D Zelda map as our running example. When we try to use a single instant NGP to reconstruct the scene, it can be visualized like this. So this overlapping blue and magenta grids are occupancy grids for rate marching acceleration. Each entry of the occupancy grid stores a binary variable indicating whether any point should be sampled inside the entry. So for example, if only the top left blue entry is 0, then no points will be sampled inside the region during rate marching. This greatly accelerates the rate marching procedure for instant NGP by skipping empty spaces. Note that the occupancy grid here has a higher resolution in the center and progressively lower resolution further away to be able to represent distance seams without an explosion in memory. But this data structure assumes that the viewer is in the center so that they don't notice the low resolution outside. And one issue that can happen when we try to use instant NGP to reconstruct large-scale seams is that the fine details far away from the center could be missing. For example, here, the trees at the top left may not be faithfully reconstructed because the occupancy grid around them has low occupancy value and low resolution. Therefore, details of these trees could be skipped during rate marching. Intuitively, one solution is just to use a larger occupancy grid with higher resolution to model this scene. However, this introduces other problems. First, the larger model may no longer fit inside the GPU memory or GPU cache because it scales cubically. Second, it could incur a higher training and rendering cost, which is hard to alleviate through parallelization. Third, a larger model is harder to transmit. And this is not ideal for features like streaming, where we want to only load the model that's feasible. So to address these problems, we propose modular NGPs. Instead of just using a larger occupancy grid, we use multiple separate instant NGPs at different locations and scales to collectively model the scene. So let's visualize this idea again in our running example. So besides the original NGP, we can additionally place multiple NGPs at different locations, like here, here, and here. Now that this NGP is larger than the previous two NGPs we placed on the left, because in our formulation, we allow different NGPs to have different scales, because different areas of the scene may have varying amount of surface details that we wish to model. So finally, here's a comparison between modular NGP and instant NGP. So as you can see here, modular NGP can represent much more details than the instant NGP. And here, one can see that modular NGPs can faithfully reconstruct this object, while instant NGP misses a certain portion of the pillar. And here, this is a modular NGP of the data center. And the camera motion is shaky here because this video is not rendered with a preset smooth trajectory like the videos that I showed you earlier. Instead, since our method supports real-time rendering, a user is using a keyboard to interact with modular NGP as if it's a 3D world model. And that's why the video looks shaky. So an obvious question is, since our proposed solution, which is to use multiple instant NGPs to collectively model the scene, is also using more memory. Why is this obvious? Why is this better than just simply increasing the size of the occupancy grid? Well, the first nice property of using multiple instant NGP is that now we have the ability to determine where to spend the fine resolution. That is visualized as the magenta grids here. So if we simply use a larger occupancy grid in the original instant NGP, then we're implicitly assuming that we want to spend all our fine resolution near the center, which is rarely the case for large-scale scenes. The second nice property of modular NGP is that multiple NGPs can be easily parallelized. So this is obviously very important for both training and inference. Third, modular NGPs allows users to do streaming. So let the red triangle represent the viewer's location. Depending on where the viewer is, we can only activate the NGP that contains the viewers for rendering. And here are a few examples. So this is convenient because an NGP will stream in only when it is visible. And this reduces the burden for both transit and memory. And here, I want to compare modular NGP with BlockNerve, which is the current state-of-the-art on city scale reconstruction. So BlockNerve takes around 10 hours on 32 TPU v3 cores to train each nerve. And in total, it has 16 or 32 nerves. And each modular NGP takes less than 3 minutes to train on a single RTX 3090 GPU. Additionally, during inference, each block nerve takes 6 seconds to render 1 frame, while each modular NGP render faster than 15 frames per second, resulting in a 90 times speed up. Cool. So that's modular NGP, a fast reconstruction method for city-scale scenes. It makes the neural fields more functional for applications like street view simulation due to the real-time performance. Additionally, its training efficiency also makes it more accessible for users because not many people have lots of TPUs. Okay, so hopefully these projects have shown that neural fields is actually one very promising way to get us to the top right goal. And I would love to talk about what I'm excited to pursue in the future. So recently, many text to 3D models have shown that it is possible to synthesize high resolution meshes given text input. And I'm very excited about this method because it makes generating 3D contents very accessible. Now, we do not need artists to spend 70 hours on a high quality mesh, and we may not need high quality scanner to generate good mesh that we can put into the robotic simulation. So what I'm interested in explore in the future along this direction is how can we use this kind of 3D generative model to generate part level 3D content. For example, we don't just want a car in the graphics engine or in the physics simulator. We want a car with its wheels and tires all separated so that we can separately control them and animate them. And the second is how to synthesize deformable objects. Now, scene-to-real is actually a very popular approach to address deformable object manipulation. So I believe if we can use this kind of 3D generative models to synthesize deformable objects, then we can make a lot of great progress on deformable object manipulation. The third is, can we train scene-to-real dexterous policy with 3D contents generated by the text-to-3D models? So for example, if we can take tau and pocket system and replace all the meshes with the text-to-3D generated meshes, will the system work? And if not, like what do we need to change in order to make the system work well? Because if it works, then we basically have unlocked, we basically have resolved the data issue from the simulation side. And then we can use reinforcement learning to solve a lot of very challenging tasks. And the fourth question that I'm interested in is how to assign physical attributes for generated 3D data so that it works well in physics simulator. For example, if we synthesize a hammer, but we just simply assign uniform mass distribution, then it would look very weird in either graphic simulation, AR application, or our physics simulator. Because the hammer, the head part should be much more heavier than the handle part. So how can we give neural networks this kind of prior when we are synthesizing 3D objects is very important to make this line of research even more functional in the future. On the accessible side, I'm also very interested in how to speed up the generation process. Because right now, the state-of-the-art text-to-3D generation generator, it still takes more than an hour to just generate one mesh. So it would be very interesting to see how can we speed up that process so that we can generate 3D contents like we generate images right now. And the second question is how to leverage the text-to-video models prior. Existing text-to-3D models oftentimes only rely on text-to-image prior. But if you think about it, when a model can generate a video, it clearly has some 3D understanding inside it. So I believe it would be very exciting if we replace the text-to-image distillation scheme that we have right now with text-to-video distillation. And I believe that will greatly lead to a lot of improvement in terms of the generated 3D contents quality. And the other question is, how can we leverage 3D data sets? So although the 3D data sets amount is very small compared to 2D images, but if we have lots of 3D data sets, can we use it to train a 3D version of clip model? Can we use it to train a 3D version of critic to perform some kinds of reinforcement learning from human feedback for the text to 3D generator? These are all unknown questions that I think have lots of potentials. And the last one is fine-grained control on how to generate 3D contents. For example, by just specifying a text to generate a 3D is still very ambiguous. And it is definitely not what a game designer wants. So by being able to supply additional input, like a style image or a specific subject, is very important, I believe, to make all these text to 3D methods better. So with that being said, this is all I have today for you in terms of the research content. And I would love to send my acknowledgement to people who are very important throughout my PhD. So the first one, of course, I want to thank Phil, who brought me to MIT. Phil and I met, well, actually, we didn't really met. He's waiting for Uber at Hawaii, probably to some party. And I was just an undergrad from a random undergrad university no one knows. And because I recognize him, so I just run super fast, maybe the fastest run I have ever had, to him and stop him. And I was like, hey, Professor Philip, I made this TensorFlow pix-to-pix implementation on GitHub, and you actually referenced it on your website. So I think maybe we should chat. And also just by accident, I'm applying to PhD programs, so maybe we can talk about that too. And Philip is so nice that he actually scheduled a meeting with me next day. And we actually walk around the second floor of CVPR just to talk about my research. And then surprisingly, he took me to MIT, and definitely that changed my life completely. So I want to thank Philip for that. And yeah, I never dreamed of being a PhD, but Philip somehow really makes me feel like PhD can be very cool. So yeah, thank you, Philip. And the second person that I definitely want to thank is Alberto. So I remember after receiving my MIT admission email, the first faculty that I screenshot with is Alberto, because the reason why I really want to work on robotics is that I think his paper with Andy and Shuran on all the grasping and the picking, pushing stuff is so cool and so fascinating. So I also just cold emailed Alberto, and for some reason he also replied to someone who has no robotics experiences. And it's my honor to actually work with you for the past few years, because I want to let you know that your research is really the reason why I'm so interested in working on these problems. And of course, I want to thank my committee member, Vincent, because if he didn't publish Single Representation Network, then maybe there's no neural fields. And then maybe I may not be able to write a thesis on this topic. And maybe I cannot get a job. So Vincent is definitely the true pioneer of this field. And every time I chatted with him, it feels like a very great recharge, because sometimes I'll be very depressed. Oh, there's no important problems anymore to work on. Industry is, winning. But then Vincent is always so passionate. And every time after chatting with him, I will feel very energetic, because he will pass his energy to me. So I want to thank Vincent for that. And of course, I want to thank my collaborators. And I have to mention Zhongyi, Pete, Andy, John, and Shuran, who I met at Google, because they essentially serve as the senior PhD student role during my PhD career, as I do not have a senior PhD student in my lab, at least for the Philips side. And they really taught me a lot on how to do research, how to think about problems, and keep high standards. And I also want to thank Wei-Chu for providing all the guidance along the way from Toronto to MIT. And now I'm very happy to see that he's going to become a faculty at Cornell. And of course, all the other people who I put on this page have taught me a lot. And what I really like is that we're not just research collaborators, we are also very close friends. And I really wish we'll stay connected even after I graduated. And of course, I have to thank ISO lab mates. So you guys are really amazing. And you guys are the first batch. I came to US by basically knowing no one. And you guys are my first batch of friends and have taught me a lot about United States. And it is very interesting to look back because I think we're all pretty different now. But I think it is pretty interesting to like grow older together and observe the difference. And I have to say the lab retreat we had last week is so impressive because there are so many houseworks, but everybody just automatically distribute all the works. Nobody complained. Nobody is commanding anyone to do anything. And by the time we left, the room is so clean. And it was amazing that how Philip can just assemble these people together and how nice these people are. And of course, I have to thank my N-Cube lab mates. So I feel guilty when Philip was introducing me earlier when he said that I set up all the hardwares. So in reality, it is always Alberto's lab members who are helping me to set up the hardwares, or they're telling me how to set up the hardwares. And they're really a bunch of people who are really smart about robotics. And every time I look at their research, I have imposter syndrome because I don't know if I'm really just working on computer vision or robotics because their research looks so cool. And they're definitely working on those demos that I think will keep winning best paper awards. Oh, also, I think they also told me a lot about United States. I couldn't forget people's face when I told them that I've been following NFL pretty closely. And I even read a book about how to appreciate football. And everyone in the lab was so shocked. And I still couldn't wrap my head around because I thought football is the biggest sport in the United States, but apparently no one in MIT really likes it, except Wei. So I guess, I don't know. So I also want to thank my family. My dad has always been my idol, and my mom has always been my top supporter. And my sister always gave me wise advice. So it is very interesting that the day I received the MIT admission email and I called my parents, they didn't answer because they were traveling. And 2 days later, they finally answered, and I told them the news. They do not seem happy at all. And my mom immediately entered into a worrying phase where she's like, do you think you're going to work a lot? And I'm like, I think probably, yeah, but I'll be happy. And she's like, Yen-Chen, actually, I don't really want you to work a lot. Like, all I want is you just to work at this small company right beside our house, and then you can come home every day. You don't really need to achieve anything. So actually, they're the other side of supporting my PhD. But it is that unconditional love that I feel very appreciated. So on the right, I also want to thank my grandma who passed away a few years ago. And I want to thank her because she still remembered to call me and congrats on my graduation, like before she lost conscious. And she's so nice. She like brought me up. And according to her, I've always been very interested in all sorts of motors or like robots of building houses in Kaohsiung. And like when I was small, he would just take me to see those robots and I would stand there for hours. So I guess I really didn't change that much. And lastly, I want to thank my partner, Layden. It is very hard to find a partner who enjoy rap music or rap concert as much as I do, who enjoy basketball and football as much as I do, who also enjoy skiing as much as I do. And I really like how you keep everyone in our small family accountable, including the dogs. So I think we all grew a lot, including the dogs, within your supervision. So I want to thank you for making me learn how to become a better partner and a better person. And lastly, I want to show these pictures to reflect my memories for the past few years. And by no means this is everything, because I was so stressed yesterday, and so I don't have enough time to make this slice look nice. But I want to thank everybody in this picture, or someone who's not in this picture, which I feel sorry about, that you guys gave me a really wonderful 5 years in the past. And I've been to so many countries, so many locations with you, and we have so many nice discussions, and I wouldn't be here without your support and guidance. So with that being said, this is the last slide of my PhD defense, and I want to thank everyone who comes here.
Great, very, very, very cool. So we have some time for questions. And so the way that this will work now is we'll first do audience questions, then we'll have a closed session with the committee. And then probably around 4 or whenever we get out, we'll have a celebration. And Alberto, where's the celebration? In here. Okay, we'll have a celebration in here, so don't go too far. And yeah, now we can do audience questions. And Yen-Chen, I'll let you lead that. Yeah, we'll use the mic.
Thank you. Yen-Chen, thanks for the awesome defense. For your contrastive work, when you were doing the dense correspondences, why would you prefer a contrastive network over something like SIFT correspondences, like classical techniques?
Oh, yeah. So in this case, SIFT correspondence can work to an extent, but it wouldn't be as robust as actually training a correspondence model with contrastive losses with a limited domain, because it really allows your model to focus on a category of objects, so that your model is basically overfit to that category, so that even for an unseen fork, our model can still work. So if you use a SIFT, then you probably wouldn't be able to associate 2 different forks of different sizes or different textures. And that's why we want to train our own correspondence model here. And I want to give credits to Pete Florence, Lucas Manueli, and Russ Drake, who actually made the first version of this model on showing how dense correspondence can be actually useful for robotic manipulation. So yeah, SIFT Fisher can work to an extent, but not for manipulation, I believe.
Thanks, Yen-Chen, for the talk and all the cool nerves. So I have a question regarding what's your thoughts on future 3D data for robotics? Seems like there are 2 ways you can get all these large scale data. You can do the nerves and scans all the real world objects, or you can use all these generative model to generate the 3D models. What do you think in 5 years would be the dominant paradigm to get all the data? And also, do you think a follow-up question, this seems to be a chicken and egg problem. We'll need all these 3D models to train and to train a generative model. Do you see this way that we can kind of bootstrapping this?
Yeah, very good question. So I think in the next few years, I believe in that the generative approach will grow much faster than the reconstruction approach, because I'm the one who actually tried to build a lot of nerves myself, and I even rented a laser scanner and stay in the lab till midnight just to try to scan something. And I can tell you, manually creating a nerve or scanning an environment is by no means easy. It actually has a lot of technical knowledge that you need to know before you can become a very good scanner or a nerve creator. So I think because of that entry barrier, I think the generative approach, which is getting better and better over days, will be dominant in the next few years. But of course, as we get more sensors, like for example, Apple Vision Pro has, I think, 12 or 16 cameras attached to it. So I think that would also be a very interesting multi-view camera resource. So I think the reconstruction approach will grow slowly, just like how it grows in the past few years. But then I think the generative approach will grow exponentially.
Okay, more questions, yeah.
So I think a few years ago, there was a paper, NeRF++, that says that even with incorrect geometry, you can use the view reflectance to kind of get inaccurate reconstruction.
Yeah.
So I'm curious in your case, since you have a lot of kind of like shiny or refractive objects, like transparent objects, what's the inductive bias in your NeRF network that allows it to get the geometry, which is really important for your downstream amplification, rather than kind of like baking that into the reflective component?
All right, now I have to reveal my secret recipe. So actually, when I'm presenting NeRF supervision, this step is super important. So I felt that incorporating the sparse point cloud from the structure from motion is super helpful. And in this case, because the objects are thin and shiny, actually, we cannot really recover many points on the object from the structure from motion procedure. But we are able to recover a lot of points on the floor. So by using these points on the floor as additional regularization to train our NeRF models, that means a lot of times when NeRF shoot a ray, it already knows that it has to hit the floor because floor is where the surface at. So then it poses a strong regularization of not letting NeRF to introduce artifacts that flows in the air. So I felt that this part is super important to make the whole thing work. And I believe this is why our reconstruction can get relatively nice geometry compared to what NeRF++ and other NeRF papers have demonstrated before.
We have a Zoom question. Okay, so Xiao Tong says, great works. How do you get the camera poses using the iPhone?
So there are two different ways. You can rely on the IMU and the SLAM system, the SLAM foreground system on the iPhone to directly get the camera poses. And I have success with that. So basically that's using ARKit to just estimate the camera poses from a video sequence. But in order to get the best results, you would just fit all the iPhone images into CoMap and perform structure from motion to estimate its camera poses. And that will usually lead to the best results. You can even fusion both. So I've also tried it by just taking the ARKit camera poses as initialization, send them into CoMap, and perform a few iterations of refinement. And that will actually work. That actually worked very well. So that's another approach.
Cool. I'll just check if there's any follow-up. No. Okay, good. Maybe one more question, or okay, yeah.
Yeah, hi. Thanks for the great talk, Yen-Chen. So you mentioned you were talking about the generative approach in terms of using 3D generative models to generate new data for downstream tasks. But I guess as you mentioned towards the end, one problem right now is that those models are pretty slow in terms of generating new data. So I guess what do you think is the sort of the biggest bottleneck in that process, or sort of do you think there's sort of one bottleneck where, once it's addressed, that whole approach in terms of generating 3D data for training is really going to take off?
Yeah, I think the biggest bottleneck right now is that we're mainly relying on 2D image prior, which is stable diffusion or all sorts of state-of-the-art diffusion models, to perform distillation for generating the 3D shape. And I think that distillation process is just very slow because each step of the gradient may not be very helpful. So I think one very promising way of accelerating that process is just to come up with ways to create more 3D data and come up with methods that rely on 3D data more, so that immediately you can generate like a prototype or like a low quality 3D content using the model you train with 3D assets, and then start from there with the 2D prior refinement. And I believe that procedure will greatly speed up the generation process, and it will also make use of both 2D and 3D contents.